Hello and welcome to Lecture 3 of Magnetic Forces and Fields in PHYS 1201. In this lecture we're going to look at the forces that magnetic fields exert on current-carrying wires. Magnetic forces are not like electrical forces. Electrical forces always act in the direction of the electric field or directly opposite the direction of the electric field. But magnetic forces are more complicated than that, and I find that the thing that students have the most trouble with is keeping the direction straight. The magnetic force on a wire is perpendicular to the wire, and it's also always perpendicular to the B field. So, if you think of this case, with the current going this way and the magnetic field up, that leaves you two possibilities: to be perpendicular to both. Either the force is straight out of the screen or it's straight into the screen. And so we decide between those two possibilities using what's called a right-hand rule. So you put your hand in this shape and you stick your thumb along the current and your forefinger along the B field, and now your middle finger sticking out points in the direction of the magnetic force. So if you do this with this picture, you're going to find that the magnetic force is out of the screen. And I'll say, this is only one way to do the right-hand rule. This actually isn't the way I like to do it. I'll show you another way in class. As we'll see, the forces on current-carrying wires usually aren't very big. But if you use a big current and a strong magnetic field, you can see their effect. So here I've set up some rare earth magnets, and I've set it up so that the direction of the B field between the poles here is that way. And you can see this red wire coming out of the positive terminal of the power source, and so the current is coming out of the screen at you. And so now if you use the right-hand rule, you're going to find that the magnetic force should be up. And indeed, when I turn on the current, you see the wire rise up, and I can push it down and it springs back up. We've mostly seen everything we need to know about the size of the magnetic force on a current-carrying wire, because we used it to define the strength of a B field. If you measure, remember, the size of the force, then you just divide it by the current in the wire and the length of the wire to get the B field strength. And so you can just rearrange that if you already know the strength of the magnetic field and you want to know how strong a force is going to be on the wire, you just rearrange it to this. However, note that this only works if the wire is perpendicular to the magnetic field. And we already saw this because these pieces of wire here that are parallel to the magnetic field have no magnetic force acting on them. That tells you that there must be some dependence on the angle between the wire and the field. And so let's look at what happens when the wire more generally makes any old angle theta compared to the B field. Then the magnetic force magnitude is the same expression but times the sine of theta. Notice, in this case, with a wire parallel to the B field, theta is 0, and sine of 0 is 0. And so this expression gives what we need it to, which is a 0 force on any wire that's parallel to the magnetic field. And this tells us that the magnetic force is largest when the wire is perpendicular to the field, or in other words, when theta is 90 degrees. Let's practice using all of this to calculate something. Here's this setup again with these two wires A and B parallel to each other. And before, in a previous lecture, we looked at how to find the B field at a point P. But that's not what we're going to do now. Now we're going to find the force that one wire exerts on the other. So let's find the force that A exerts on B. So this is a totally different situation. When we were finding the field at the point in between, they were both source wires. But now we're thinking of wire A as the source of a field down here where B is, and B is a probe responding to that field. So let's first think about the direction of that field. As before, the right-hand rule is going to tell you that the field is out above wire A and into the screen below it. And so down here where wire B is, there is a field into the screen produced by wire A, and so I'll call it BA. And wire B is going to respond to that. So let's think about the direction of the force on wire B. So again, do the other right-hand rule. Stick your thumb in the direction of this current and your index finger in the direction of this B field. And you're going to conclude that the force that we're interested in is up. All right, now let's start working through all the magnitudes. So first we need the magnitude of the B field down here at wire B. So we know how to calculate the B field due to a wire, and so I'm going to say BA is going to be mu naught I. Well, here's where a lot of people mess up. Remember, the source of this field is wire A, and so the relevant current here is IA. And now this R here is the distance that we're interested in. Over here we are 2 centimeters from wire A. And so now we can go ahead and just plug in numbers. Again, we've got a 2 pi in the denominator, so it's going to be convenient to work with the exact expression for mu naught, because then we'll get all sorts of nice cancellation. And this, again, we can pretty much do in our heads, because all of that cancels out to a 2. We have 2 times 10 to the negative 7 over 0.021 times 10 to the negative 5 times 8. We get 8 times 10 to the negative 5. And check the units. Amps take out amps, meters take out meters, and we're left with Teslas. Now let's find the force. So first of all, one part of this is going to be very simple. The current is straight to the right, and the field is directly into the page. And theta is the angle between them, so theta is 90 degrees, and sine of theta is 1. And so we're just going to have that FA on B magnitude is just going to be ILB. And the relevant I now, this is the current in the wire that is responding to the field, and so this is IB. And so we have 6 amps times this length of 5 meters times our 8 times 10 to the negative 5. And check the units. A Tesla is a Newton per amp meter, and we have amps and meters over here, and so we do indeed get newtons as we better. I just want to point one more thing out about this. If you now wanted to calculate FB on A, the force that wire B exerts on wire A, well, the right-hand rule would tell you that there is a field out of the screen up here. This is B due to wire B. And then the other right-hand rule, thumb, index finger out, tells you that the force on wire A is down. And if you worked through the magnitude by all these methods, you would find that it's exactly the same. But of course it has to be, because Newton's third law still works, and so whatever force A exerts on B, B must exert a force back on A that is equal in magnitude and in the opposite direction.